don't think there's anything glaringly new today like the difference quotient was yesterday, but I knew the difference quotient would be brand new to you, so I wanted to give a full day to that. Even and odd functions, okay? Not to be confused with even and odd degree polynomials. Yes? When you're talking about even and odd degree polynomials, you're talking about kind of this sort of stuff. Is that an even degree or an odd degree polynomial? Even. Even degree. And I'm only bringing this up so you don't confuse them. And this, with opposite end behavior, was an odd degree polynomial. Remember that from last year? Yes, okay. That only applies to polynomials, those rules about end behavior. And that's the degree of the polynomial. What we are talking about is essentially entirely different. We could draw some connection between the two. There is some underlying connection, but for all intents and purposes, this is something totally different. This applies to all functions, not just polynomials, although I'm looking at my examples here at the bottom and I'm like mad at myself because I did do all polynomial examples, but I'll make up one that's not a polynomial before we leave here. So essentially, and you did this again last year, and I'm just further clarifying the difference between the two. Even and odd functions, if the function is symmetrical to the y-axis, okay, so let's take an absolute value function, okay? That's not a polynomial, so to talk about the degree of that being even or odd is not even a point. But that is a function that is symmetrical to the y-axis, so that is an even function. This is f of x equals the absolute value of x. So from a visual graphing standpoint, you get that symmetry to the y-axis. Algebraically, if you're asked to show whether or not something is even or odd, you plug in negative x. And when you plug in negative x, if it ends up equaling the original function, again, once you simplify it, then it's even. So take this one for example. If I plug in negative x, f of negative x equals the absolute value of negative x. And the absolute value of negative x is always going to be the same thing as the absolute value of regular x. Yes? So it ends up f of negative x equals the original function. And when that happens, it's even. Okay? Odd, it's symmetrical to the origin. So, trying to think of something that's not a polynomial that's symmetrical to the origin. I think I got one. I think, it's a little trial and error maybe. I think your basic rational graph parent function is going to be, yeah, okay, is going to be symmetrical to the origin. So, I don't know if you remember what this parent graph looks like, but I'm going to give it to you. It's kind of in two parts, rational graphs like this. Does that look familiar? Yes, no? Okay. So being symmetrical to the origin, and I wrote this in parentheses, two different things in parentheses below. Same graph after reflection across the x and the y-axis. So if you reflect it across the x and reflect it across the y, you'll be back to the original graph. The other way of looking at it visually is that it looks the same right side up as it does upside down. So if you look at this graph, it is in the first and third quadrants right now. If you flip your paper upside down, you're looking at the same graph, first and third quadrants upside down. So if something looks the same right side up versus right side, or right side down, right side up versus upside down, then it is symmetrical to the origin. And if that is the case, it's an odd function. Algebraically, again, you still plug in negative x, but you're not going to get the same as the original. You're going to get the opposite of the original. meaning the original equation negated. So on this one, if I plug in negative x, that's 1 over negative x. And we all know that whether the negative is in the numerator or the denominator, that's the same thing as really just having a negative out in front. So you see that it's the opposite of the original? Yes? Okay? And so for that reason, we have an odd function algebraically. So that should all be review. So algebraically on this one, we're just going to check to see by plugging in negative x for all of our x's, and then simplifying. So what is negative x when we square it? X squared. And then plus negative x is just going to be minus x. Now, is that an exact match to the original? No. Is it the opposite of the original? Is it a negated version of the original? No. A negated version of the original would be negative x squared minus x. Yes? And that's not what we have here. So this one is neither. It's not an even function. It's not an odd function. It's neither. Okay? If we're talking about the degree of the polynomial, is this even or odd degree? Even. Very good. You can't be neither when it comes to an even degree polynomial or an odd degree polynomial. You cannot be neither. Does that make sense? But as far as even and odd functions are concerned, you can. So I'm just going to offer up a graph of this just to wrap our heads around it. X squared plus x. And look at what this function looks like. It's basically a parabola that looks like it's been shifted a little bit to the left, right? Okay. So obviously, because it's shifted a little to the left, it's lacking that y-axis symmetry. It's certainly not the same right side up as it is upside down. Okay, you're looking at two different graphs that way. So it's not even or odd function, but as far as degree is concerned, it's the same end behavior, so it is an even degree, which Jalen told us she knew anyway because that's the leading exponent is even. Okie doke? Any questions on that? Okay. Try 51 on your own. Taylor, what did you get for 51? Even degree. So f of negative x when we simplify, negative x squared is going to cancel that negative. Minus, when I raise this to the fourth power, make sure you're doing that first. Do not fall into the trap of the double negative becoming a positive, because that would be doing subtraction before you're doing exponents, which is a big no-no in PEMDAS order of operations. So raise that to the exponent first, which again is going to cancel out that negative. And if you look at that, that is exactly the same as the original, and so that is even. Good job. Anyone get number 54 yet? Connor, what'd you get?
54.
This one. Did you get even or odd?
Yes.
Odd. So we plug in negative x. And when we cube this, the negative's still going to be there, yes? So I'll just bring that negative out in front, negative 2x cubed. Minus 6 times, when I raise this to the 5th power, that negative is still going to be there. I put the multiplication there, so it's negative x to the 5th. The negative 6 times the negative this is going to turn it into a positive 6x to the 5th. And this is exactly the opposite of the original. If I were to negate the original here, it would be negative 2x cubed plus 6x to the 5th, and that's what we have. So it is exactly the opposite of the original, and so therefore it is odd. Good? And then I added this number 56, so go ahead and try that one. Okay, Adam, what'd you get for that one? You got even. So if I plug in negative x and go through, this negative is just going to cancel when you square it. Square root 1 minus this negative is just going to cancel when you square it. And if you compare that to the original, exactly the same. So even is correct. I sort of come up with 2 more versions of this. So I want you to try these 2 examples down here and see what you come up with. Stephanie, what do you think about that first one? Neither. Raise your hand if you also got neither. Okay. So, did you all get this? Yes? Okay. When you look at a negated version of this, if I put a negative out in front of that,
how do I simplify that? If I were to kind of check, if I were just negating this and taking the opposite of this, so I threw a negative out in front, how would I simplify that? Do I distribute the negative inside the radical? Or is the negative just out in front and then what's underneath the radical stayed the same? Yes? So this is exactly opposite of the original. This is an odd function. Okay? Because you only did polynomials so far, and I'm just hypothesizing here that this is why the majority of you misanswered that, you're used to every single sign flipping if it's negative, right? And that's true in polynomials, because when you negate a polynomial, you have to distribute your negative throughout the entire thing, which in essence flips every sign. That's not the case for all functions. Okay? When you negate a radical, you pretty much put the negative out in front, and now it's the opposite of what it was. You do not distribute the negative through here, so that wouldn't change. Is that clear? So this one, we did come up with the exact opposite of the original, because when you negate this, that's what it becomes. You don't have to distribute that negative. So this is odd. And therefore, on the second one, what is that? Also odd. It is the exact, it's just a negated version of the original. So this one is also odd. Let's take a peek at those functions. You would have no idea visually what these look like on your own, but if I take x to the third, I'll do this first one. Square root of 1 minus x squared. Now, something very, very small happened right in here, and that's the limit of the graph. This range, or domain rather, is only between -1 and 1. So I'm going to change my window and go from -1 to 1 and -5 to 5 just to zoom in a little bit. You tell me, why is the domain only between -1 and 1? Numbers outside of that domain, like let's say a number 2, would cause what to happen? A negative under the radical. So anything greater than 1 or less than -1 is going to create a negative under the radical. So first of all, understanding the domain here. This graph is only from -1 to 1. And I don't even need -5 to 5. I'm going to change my window all the way -1 to 1. And here's what's really happening once we zoom in there. And so look at that weird pattern in the first and third quadrants. I flip it upside down. Does it look exactly the same? Yes. Hence the reason it was an odd function. Okie doke? So I guess the new learning point is be careful, because you're now checking for even and odd functions outside of just polynomials. It's not necessarily just all the signs are flipped, which was the general rule you were making for polynomials, because that's what that was. Liam, open your eyes. Good morning. All right, flip over to, well, I have your steps down here. You're kind of plugging in -x, and then if f of -x equals the original, it's even. If f of -x equals the opposite of the original, it's odd. What do I have on the back? Hopefully not a lot. Oh, good Lord. All right. More with interval notation. Okay. The domain of this function is going from -infinity to positive infinity, right? Okay, -infinity wants interval notation where applicable, so that would be the way to write it in interval notation. The range, the lowest y value, -1, 2, 3, 4 to infinity. What sign around the -4? Parenthesis or bracket? Bracket. It's a bracket because I heard a couple people say parentheses. It is a bracket. because that's the lowest value it ever reaches, and that's a solid dot there, so it's actually reaching negative 4. X-intercepts, we have 1 and 7. I'm going to do that in set notation, just listing those x-intercepts, because interval notation wouldn't be appropriate there. Y-intercept, 1, 2, 3, 4. This should all be easy stuff. Intervals on which f is increasing. What do you think about that? Ellie. 4, comma, infinity. What kind of signs? Very good. How about decreasing, Liz? Very good. From 0 to 4. Parentheses. Constant. Kendall? Negative infinity up to 0. Parentheses, because that's what we do there. Always with slope type stuff. The number at which a relative minimum occurs. When they're saying the number at which, as opposed to the value of the relative min, the value of the relative min we talked about yesterday is the y-coordinate. The number at which it occurs, that's the x-coordinate of your relative minimum, which is here. So at 1, 2, 3, 4. So at 4 would be your answer for that one. The relative minimum, I'm going to put value after that. That's going to be the y-coordinate of negative 4. So again, just paying attention to how they're phrasing it. F of negative 3, function notation, 1, negative 3, as your x-coordinate yields a y-coordinate of 4, so that would equal 4. Values of x for which f of x equals negative 2. So if they're telling you that f of x equals negative 2, which coordinate are they giving you? The y. So if you look at y's at negative 2, the values are here and here. Those are the x-coordinates. So that would be an x-coordinate of 2, 3, 4, 5, and an x-coordinate of 6. So 2 and 6. And is f even, odd, or neither? Since we're looking at it, does it have any symmetry to the y-axis or the origin? No, so neither. Okay, a new type of function for you is a step function. The symbols of the parent graph are like these kind of double-edged brackets, and this is going to pop up throughout the year, so don't see it in a couple weeks and say, I have no idea what those symbols mean, because we're going over it now. This is the greatest integer function. So what it is asking for, how you kind of apply those symbols to the x value, is you answer with the greatest integer less than or equal to x. So for example, if I wanted you to do f of 5.2, what is the greatest integer less than or equal to 5.2? What's the greatest integer less than that? 5. If I asked you to evaluate f of 5.9 in this function, what is the greatest integer less than or equal to 5.9? 6? Is 6 less than 5.9? It's not telling us to round to the nearest integer. It's telling us to round down always, essentially. Round down to the nearest integer, so that would be 5 as well. So that's going to take some getting used to, because I know that your instinct is to round. What if it's f of 5? What is the greatest integer less than or equal to that? 5 as well. Okay? How about f of negative 2.1. What's the greatest integer less than or equal to that? Good. Adam says negative 3. Again, resist the temptation to round to the nearest integer. You have to go to the nearest integer less than that. And negative 3 is less than that. Negative 2 is unfortunately greater than that. So you'd be wrong with that answer. Okay, so also be careful in the negatives where this can mess with you. So why did I just do those? I don't know why I made them up off the top of my head because I had a few examples there. Very quickly, this one is 4. What's the second one? 5. And the third one? 3. Okay? Now, what does this look like? So on your calculator, and you don't need to do this, just watch. Under your, I believe it's the math, yeah, I wrote where to find it here. If you go to math, I'm going to type it in and look at the graph, see what it looks like. So if I go to math, I can get this symbol by going to my number menu. So I wrote that. And then INT. It's for integer, obviously. This is the greatest integer function. So if you plug that in, it'll say the words INT, but symbolically in math, in a textbook, you'll see that. If I do zoom 6 here, now maybe you can see why it's called a step function. Yes? I'm going to zoom in and I'm going to look at this from negative 5 to 5. Okay? So why is it a step function? Let's take, if you plug in 1, f of 1 is 1, f of 1.1 is 1, f of 1.7 is 1, f of 1.9 is 1, f of 1.99999 is 1. Yes? And then as soon as you get to f of 2, you jump. Okay? You can't see it on the graphic calculator, but at f of 1, would this be an open circle or closed circle at the end of that step? Closed, because f of 1 is 1. And so at f of 2 is 2. So what's at the end of this step? An open circle. Okay? Because f of 1.9999999 is still here. Everything up until that open circle, but as soon as we hit 2, we jump up. And as soon as we hit 3, we jump up. So that is something, a detail that your calculator is not going to show. Okay, so make note of that. Alright? So just a new type of function that will come up that we will also work on transformations with. You might see f of x equaling this. What would that do to our function? Shift it up 1, yes? Okay, what would this do to our function? Move it left 1. Good. What would that do to our function? Which did you? Reflect it horizontally over the y-axis and downward. So here you have to be careful of your solid endpoints and your open endpoints. When you flip this, your solid's going to be there, your open's going to be there. And your solid here, open, solid, open, so on. Does that make sense? Okay? So you'll see those symbols, and it's the greatest integer function. So when you're applying those, kind of like you would, as far as PEMDAS is concerned, you apply those symbols at the same moment you would apply absolute value signs. Except it's not an absolute value symbol. It means something totally different, and you've never seen this before, correct? So it's new, but when you're thinking about what is the value of it, simplify inside, and then take the first integer that's less than that number inside. Okay? Greatest integer function. Which actually is kind of a name that throws us off. Because greatest integer function, yet you're taking the first integer that's actually less than it. Right? So just be careful of that. All right, your homework is there at the bottom.